Okay, so we've been talking about acid and bases, and we've seen a number of different sort of formulas in terms of pH, acidic, and all that good stuff. So a couple of reminders of stuff we've been talking about here in this chapter as we kind of head towards the end of it. And go here. So remember that the Bronsted-Lowry definition of an acid is that proton donor, and the base is the proton acceptor. And as we talked about with that, that does bring out basically our conjugate acid base pairs, where the acid is basically related to the conjugate base on the other side of the equation, and the base partner on the other side of the equation is the conjugate acid. Remember that the only difference between those two things is just one H plus is the only difference that there has to be between them. And that's because basically the acid is donating its H plus over to the base. And what we end up with on the other side of the arrow there are guys that are basically the difference there of just one H plus. We talked about sort of Kw as well, which is the equilibrium constant for water, which is H plus, and OH minus, which equals 1 times 10 to the minus 14. Remember, we could use this to solve for either one of these. It's basically the same calculation regardless of which one you're doing. 1 times 10 to the minus 14 divided by OH minus for the H plus. And if you got the OH minus there, that is 1 times 10 to the minus 14 divided by the H plus concentration there. And we could use that if we wanted to determine acidic, basic, or neutral by comparing the H plus to the OH minus concentration. And then obviously whichever one is larger is what it would be. So again, if the H plus is larger, that would be an acidic solution. If the H plus was less than the OH minus, that would be basic. And if they basically equaled each other, we would end up with a neutral solution with a pH there of 7. Now, we also talked about the pH scale. The pH scale runs from 0 to 7 to 14. Below 7 is acidic. Above 7 there is basic. And 7 there is neutral. And 7, again, is sort of our center point there. If you kind of go below 7, it becomes more acidic. You kind of go from 7 heading towards 14 there. It becomes more basic in that direction. We talked about that. That's usually the scale most people have in their head. So, one way to determine if something's acidic, basic, or neutral is to calculate the pH. And that is done by taking the pH is equal to minus the log of the H plus concentration. We also talked about a similar scale to pH, which measures the OH minus concentration, which is the POH minus the log of the OH minus concentration. The relationship between these two is if you take the pH plus the POH, that will equal 14. So this gives you a way, again, if you know the OH minus concentration, you could get the POH and then subtract 14 to get to the pH without necessarily having to even use this equation, RKW. A couple other things that we talked about was if you actually have the pH value given to you, from that, as the name implies, you can get the H plus concentration, and that is the inverse log of the minus pH. And I think as we talked about on our calculators there, that typically will put up like a 10 and a caret when you do that. And you want to make sure you make it negative here. And you can also do that with the POH value. You could get the OH minus concentration there by taking, again, the inverse log of the minus POH. And again, when you do that inverse log, it will put usually a 10 and a caret up on your calculator there. And that's where you can calculate it. So really with, sort of all these different sort of formulas, it does give you, depending on what you're trying to solve, a few different ways you could kind of approach it. There's places where you might not even need to use KW to solve a problem. You could just use really these last few equations. You could still use KW to solve some problems. Just sort of the path that you choose as you go to solve these guys. They all really should get you to the same spots if you do the calculation right. And I think the last couple of things we talked about a number of times is our calculators. And remember that pretty much for, all these sort of formulas down here. If you have a display calculator, as we were talking about, you do pretty much just type everything into your calculator just the way the formula is written. And remember, if you really have a non-display calculator, you need to kind of roll backwards, usually in starting with the number, and kind of do the equation backwards there as to how you put it in. Any questions on any of that stuff that we talked about here? Okay, so I think we are somewhere. Let's see here. I think we're on this example here. So why don't you give it a go? The pH of the solution is 3.14. What's the H plus? Why don't we do a few everything just to make sure? Let's do OH minus and let's do POH. And why don't you make sure if it is acidic, basic, or neutral. So take a couple minutes, see what you come up with, starting with a pH of 3.14. See what you come up with. Okay, let's take a look. So since I have a few more things onto this one, there's a few different ways you could approach, but we'll just go with the original question here, which is what is the H plus concentration? So remember in this case, when we do have the pH, because you have the pH, that means you can get the H plus concentration directly from it. And again, that is the inverse log of the minus pH. So again, shift or second log on your calculator. Again, that usually will put up a 10 and a caret. You want to make sure you make it negative 3.14. And it looks like if we do that there, 3.14 negative and inverse log there. Looks like we end up with a 7.2 times 10. 1, 2, 3, 4, minus 4. We do need molarity here as it is a concentration. And a reminder that when we're going backwards here, we had 2 decimal places. Does give us that 2 significant figures here in the concentration. And again, a reminder that your calculator may not give it to you in scientific notation. Again, mine gave it to me as 0.000724436. Any questions so far on that calculation there? Okay. We also are looking for POH, which is pretty simple. Again, the pH plus the POH is equal to 14, which means really the POH would be 14 minus the pH here, and that gives us 14 minus 3.14, and that's going to get us a 1086 in terms of the POH. That takes care of that. That takes care of that. OH minus, again, because you have that, you could use KW. Because you have this, you could do the inverse log of the POH here. Minus POH. Again, that would be a 10 and a caret minus 10.86. And that would get you 10.86 negative. Shift the log. Looks like a OH minus concentration of 1.4 times 10 to the minus 11. Again, you do need molar here. As it is a concentration, that takes care of that guy. Again, you could have done the KW and put 1 times 10 to the minus 14 divided by this guy. You should get pretty much the same answer. Is it acidic, basic, or neutral? Here and always, when you have all these values here, always look at the pH. And the pH here is 3.14, which means it is less than 7. And that means it is acidic. Any questions on any of those steps there? All right, let's try another one then. In this case, we'll just do whatever it asked here. We have a pOH of 5.67. What is the OH minus concentration? So just solve for the OH minus concentration in this case. From that, OH means that you could get your OH minus concentration, which is what it's asking for. Really is the same calculation, the inverse log, again, of the negative pOH. Second or shift button, top left corner of your calculator, and log. We'll put that 10 in a caret, and then again, make sure you make it negative 5.67. And looks like, in this case, 5.67, make it negative. And a little shift log. Again, I have a one you have to do it backwards. So I started with the number there and made it negative, then did shift log, and 2.1 times 10 to the minus 6 molar. Again, 2 decimal places, 2 significant figures in the concentration. Any questions on that calculation there? All right. Any questions on how to calculate pH, pOH, H plus, OH minus concentrations? Okay, then now not all the time will you maybe necessarily be given, kind of the generic, if you will, H plus or OH minus. So a lot of times you will, but you could be given perhaps a pH or a question where it asks, hey, what is the pH of a strong acid or even a strong base? And remember, there are certain strong acids that we oftentimes think about. So some of those strong acids, hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, perchloric acid. So these are all some very common strong acids. A lot of strong bases actually have OH minus in the actual formula. So things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and so forth. If you look on the periodic table where like sodium is and potassium, then there's calcium. If you kind of like go this way, this way, and this way, and add OH to those guys, this is where a lot of strong bases really come from. So, what happens if we did have something like hydrochloric acid here in solution? The hydrochloric acid, because it's a strong acid, means it's a strong electrolyte, which means when it goes for a swim, it will 100% break apart into H plus and Cl minus. And basically, in solution, that is 100% of what you have floating around. You have pretty much none of these guys together. It's all the H plus and the Cl minus. This is why it is a strong acid, because when it goes for a swim, it generates a lot of H plus very quickly. That's kind of your definition of an acid, something with the ability to produce H plus in solution. All it has to do is go for a swim, produces a lot of H plus very quickly, which is why it's considered really a strong acid. Now, once we want to know the pH of this, let's say we had a 0.2 molar solution of HCl. We could kind of use what we talked about with solutions, sort of the relationship here. It is the H plus that's really important in terms of calculating the pH, as our pH equation is minus the log of the H plus. So what we really want to know is what is the concentration in that solution of the H plus. And because it's a 1-to-1 relationship between those two, the concentration of the H plus would also be 0.2 molar, which is really all we need to get to the pH, because now we can put that in there and we will know this is minus the log of 0.2 molar. And again, if we put that into our calculator, we will end up with a pH of 0.30, which is definitely acidic here. 0.30 here in this particular case. Sure. Oh, sorry. Make sure I punched that in right. I think I might have thrown both in. Let's just double check real quick. I did. Sorry about that. It's actually 0.70. It's kind of like 3, but not so much. So 0.70 is actually the right number there. Didn't look right to me there when I did it. All right, perfect. Obviously, it's still acidic, obviously, in this case, which is what we would expect in terms of a strong acid. So sometimes you may be given the formula, and really what you need for an acid is to figure out the H plus concentration. And really, for something that's a base, you need the OH minus concentration to help you out. So why don't you take a second here and calculate what is the pH of a 0.025 molar perchloric acid solution. Again, here, perchloric acid is a strong acid. So take a second here and see what you come up with. Let's take a look at this. So knowing again that this is really a strong acid, when we would have this, just like the HCl, it would 100% break apart into H plus and ClO4 minus, which is perchlorate. It is really, again, the H plus is most important in terms of figuring out the pH. So we could do our relationship here again, since it is in this particular case, a 1-to-1 relationship. We do know that the OH minus concentration, or the H plus concentration, is 0.025. And again, that would be all that we needed. We could go into our pH minus the log of the H plus, which gives us minus the log of 0.025. And that would yield us, I see something in the chat box, so hopefully let's see what we get here. 1.60 looks good. And that again would be an acidic pH, which is what we would expect here since this is an acid. Any questions on that one? Now, what happens if we have, say, a strong base like sodium hydroxide and we wanted the pH of 0.025 molar sodium hydroxide? It would work the same way. Sodium hydroxide, which is a strong base, would also 100% break apart into ions. And again, you would have none of these guys together, pretty much 100% everything on this side. And in this case, in terms of figuring out the pH, we don't really have the H plus, but it is the OH minus concentration that would help us out here. That would allow us to get to the POH and then to the pH. So if this was 0.025, just like before, a 1-to-1 relationship here, 0.025, remembering that that is the that is the OH, which means we could calculate the POH here, not the pH. And we would get minus the log of 0.025. That would yield us a 1.60. Now, for some reason, you thought at this point that you were calculating the pH. That number definitely should not make sense to you because that would be an acidic pH if you were confused. The pH can be found by taking 14 minus the POH, which means 14 minus 1.60 yields us a 1240 pH. And that does make sense. 1240 is definitely above 7. It is definitely basic. And since sodium hydroxide is a strong base, I would expect, obviously, my pH there to be in the basic range. Question on that one there. Now, just to show you, if we took even the same concentration here, but let's say we had something like calcium hydroxide, which is sort of a strong base, we'll assume. If we have something like calcium hydroxide, when it breaks apart, we will get a calcium ion, but we will actually get 2 hydroxide ions, which means, again, it is the OH minus that's important for us. This would be 0.025 molar, but in this case, it's now a 1-to-2 relationship. So remember that basically we need to multiply the concentration by 2, gives us 0.05 molar as our OH minus concentration. We then could go into our POH here, minus the log of 0.05, gives us a POH of 1.30 POH. And then obviously to our pH, subtracting 14 from that, we yield, it looks like 1270 as our pH. So here again, remember, if it's not a one-to-one relationship, you do have to adjust the concentration correctly. Basically, we get twice as much hydroxide for every calcium that we toss into that solution. Any questions on that there? Or questions on how to do it if it's a strong acid or strong base? For the most part, if you actually see a formula in our class, it's probably pretty safe to assume that it's a strong acid or base. A weak acid or weak base, the calculation is much, much more complicated. So, if you are given a formula, probably a pretty safe bet in our class here that, it's probably a strong acid or strong base. And the key would be just get the proper H plus or OH minus concentration. Any questions on pH, any of those things there? Okay, so to finish up this chapter here and really the general chemistry part of the course here, we're going to finish up talking about buffers and what buffers are. So let's first talk about a buffer. A buffer is a solution that resists changes to pH even when you add acid or base to it. So the sort of first misconception that people have about a buffer is they think that it is always a neutral solution, and it is not. You can make a buffer at any pH you want. Anywhere from the pH scale there of 0 to 14, basically. And basically what it means is when you make that buffer, it will be able to maintain its pH even if you add more acid or base to it. So if you made a buffer at a pH of 9 and you added some acid or even some base to it, the pH would change a little, but it will basically still hang out around the 9 pH that it started at. Same thing if you made a buffer at a pH of 3. If you added some acid or base to it, it will basically be able to maintain that pH around a pH of 3. You will not see a tremendous big jump in the pH if you made a correct buffer, I guess is the way to say that, if you made a good buffer. So for example, if you made that buffer at a pH of 3 and you added some base to it, you would not see it go from a pH of 3 to like a pH of 12. Maybe it goes up a little bit, but it will not have a giant jump in pH, or it won't drop pH a lot if you add acid. So what is a buffer made out of? A buffer is made out of basically one of two combinations: a weak acid and its conjugate base, or it's sometimes referred to the salt of its conjugate base. Or you can make a buffer out of, if I can get it right, or a weak base and the salt of its conjugate acid. You absolutely cannot have a buffer that is made of a strong acid or base, strong base. So buffers cannot be made up of strong acid or strong base. There has to be weak acids or weak bases, because when they are weak, they set up an equilibrium, which means you're able to keep both things in solution. You're able to keep the weak acid and its conjugate base in the actual solution floating around together. And that's what makes it a buffer, is they're actually both in there together. So you got your weak acid floating around and its conjugate base. Or you're able to keep the weak base in solution because it sets up an equilibrium and its conjugate acid. So again, either you got your weak base plus its conjugate acid. A strong acid or strong base, like we just talked about, like HCl, is not able to do that. If you put something like HCl in, is going to 100% break apart. All you will have is H plus and Cl minus. You won't have an acid part and a base part. What makes a buffer sort of able to work is both of those things are in the solution to begin with. So you basically have an acid part to the buffer, and you have a base part to the buffer. Again, both of those things in the solution to begin with. So for example, if we took hydrofluoric acid, which is a weak acid, when it breaks apart, it will mainly stay together as HF, and we will get H plus and F minus. This is a weak acid. And is conjugate base. Again, the difference between these two, just one H plus, which is again what you need basically for those guys to be related to each other. So if we were to make a buffer of that, we would have some HF guys floating around in there, which is really the acid part of the buffer. We would also have some F minuses floating around, which is really the base part of the buffer. So kind of what we're talking about here. And again, both of those things are able to stay in that solution because of the HF being a weak acid, able to set up that equilibrium. So how does a buffer sort of really work? Well, let's talk about sort of what happens if we were to put an acid or a base into a non-buffer solution. So let's go with a non-buffer solution. And we'll do our good friend water here. So water is not a buffer. And if we were to take a strong acid like hydrochloric acid and throw it into water. So if we took a strong acid like HCl and we put it into water, what would happen is, as we talked about on the previous slide, that hydrochloric acid will 100% break apart into H plus and Cl minus. So what does that mean if we were to kind of look at our little beaker here when we did that? So if we did that and we tossed our HCl into this solution here, we basically will have H plus, H plus, H plus, H plus, H plus. We'll have some Cl minuses. Again, none of these guys will still be there. It's all one-way street. That's pretty much what we have. So if we just happen to look at, what affects pH, obviously what affects pH is, since it is minus the log of the H plus concentration, it is the H plus concentration. So if we look at what happens when we dump that strong acid into sort of solution by itself like water, we have just produced a lot of H plus. And what we see is that the H plus concentration increases. That means, by the way, that the OH minus concentration goes down as they're opposites of each other. And we would expect the pH to go down a lot. We would expect a big drop in the pH in this case. Again, we have a lot more H plus, so we would expect that pH to go down. So for example, if this was say a pH of 5, and I'm sorry, let's say water, for example, pH of, well, it might be 5 actually, but we'll say water pH of 7 here. Nice clean water, I suppose. And we added the HCl to it, we would see perhaps the pH go from 7 all the way down, maybe to 2 or 1 or something like that, depending on how much you add. We would see a pretty big drop in pH. So, for example, here, if we started at 7, maybe it drops to 2-ish or so, a really big drop in the pH because of that increase in the H plus concentration. Any questions on that there? Now, what would happen if we, to our same water, which again is not a buffer solution, we added a strong base like sodium hydroxide? When we add sodium hydroxide again to our water, which is a non-buffer solution, we will get 100% sodium ions and chloride ions. Not chloride ions, hydroxide ions would be better probably. Try that again. That should be OH minus. Try that. There we go. And again, here we would have 100% these guys in solution, none of these guys together. So if we visually sort of drew it here, hypothetically speaking here, we would have a lot of sodium ions floating around. And we obviously would have a lot of hydroxide ions floating around. And again, the same idea here. We have just created a lot of free OH minuses in that solution. What is that going to do? Well, if we created a lot of free OH minus concentrations, that means the OH minus concentration went up. Also means the H plus concentration went down, and we would expect the pH to go up. Again, we created a lot of free H plus really quickly here. I'm sorry, OH minus really quickly. And again, in this case, for example, if we started, say, at a pH of 7, maybe it jumps to like a pH of 12 or 11, something like that. A pretty big jump in the pH here, again, because of the increase in the amount of free H plus. Those are really the things in solution that affect the pH. It is the amount of free H plus you got floating around, and really the amount of free OH minus that you have floating around. Those are really the things that do affect, really the pH of a solution. So any questions so far on what's happening in a non-buffer situation? Again, here we would expect a pretty big jump in pH when we add acid or base, because we're creating a lot of H plus really quickly and a lot of OH minus really quickly. So let us take a look then at what would happen if we actually added these same two things to a buffer solution. So you could choose a lot of different buffers. Acetic acid, sodium acetate, it's a very common one, but we'll just use the one that we're just talking with there. We're going to take a buffer and we're going to make this buffer out of, we'll go with the HF, which is our hydrofluoric acid, and our sodium fluoride. So this is our buffer. And what that means is both of these guys are in the solution to begin with. The HF, which is hydrofluoric acid, is our acid part of our buffer. The sodium fluoride is the base part of our buffer. This is HF, really, the things that are really doing the action, if you will, are actually these two things. That is our acid, and that is its conjugate base, right? Difference here is 1H plus. Why do we call this a salt? Because it has sodium there to balance out the charge, not really doing anything other than balance out the charge. But that's why it's sometimes referred to as the salt of its conjugate base, because the sodium balances out the charge. But the really two sort of active participants here in this buffer is HF and F minus. So what we're starting with in this case is an actual solution that has, this is our buffer solution. It actually has some HF together, minus, and it has some HF guys floating around. It also has some F minuses floating around. It has both of these guys in that solution to begin with. And that's really super important for how a buffer is able to work, because it's able to keep both of those things in solution, an acid part and a base part. It's really able to help a buffer actually perform its sort of duties. So let us say we took our hydrochloric acid, like we did in the previous example there, and we're now going to add our HCl here. So we're going to take some HCl and we're going to drop it into our buffer at this point. First off, when we add HCl, HCl is an acid, When you do that, it's going to react with one part of the buffer. So since HCl is an acid, it's going to react with the base part of the buffer, and we're going to get this reaction where hydrochloric acid will react with this sodium fluoride, which again is our base part of our buffer, really the source of these guys that are in that solution. We're actually going to get a double displacement reaction is going to happen. That's a positive, negative guy, positive, negative guy. These two guys are going to swap or become partners. These two guys will then become partners, and we will create HF and sodium chloride in this particular case. And this is the reaction that we actually will see and will perform here. So again, our strong acid that we're adding will react with the conjugate base in this case, and this reaction will take place. We do see a couple of interesting things. One thing that we make is actually the HF, which was in the buffer to begin with. It's part of the buffer. We actually make some more of the acid part of the buffer, which clearly if the HF was there before and we made a little bit more of it, it's not going to mess up the pH. We also make this sodium chloride here. This is a salt, and this salt is one that came from a strong acid and a strong base, and really is what is referred to as a neutral salt, which means it has a pH of 7. It's not going to affect the pH. But it's actually what we do not see on the right-hand side here that we did see in the previous one. So if we go back and we take a look, when we added HCl to water, we produced a bunch of H pluses. In this particular case, absolutely, if I can find my thing, there it is, absolutely no free H pluses were formed. And that means that we did not create any more H plus in that solution than we had to begin with. There really is at the beginning here some H plus floating around, and there was there at the beginning, and we still have the same amount really there at the beginning, but we didn't create any more, which means what ends up happening is the H plus concentration remains relatively constant. And because the H plus concentration remains relatively constant from where it began, we will also see that the pH will remain relatively constant as well. So when we add an acid to a buffer, it will essentially make part of the buffer. And really what we're preventing is this free H plus from coming in here and basically being free and floating around. It actually gets gobbled up by the F minus, making more HF. It doesn't allow it to be free anymore. That keeps the H plus concentration relatively constant, and the pH remains relatively constant as well. I say relatively constant because if you actually put a pH meter in a buffer solution and you add acid to it, you would see the pH go down, but it won't go down by giant amounts. So maybe we started at a pH of 6, maybe it goes down to a pH of 5.8 or 5.9, but it won't go from like a pH of 6 all the way down to like a pH of 1. Any questions on that there? So what happens if we add the base to this buffer? Well, if we add the base to the buffer, we'll add the same one we did over there, which was sodium hydroxide, which is obviously a strong base. So if we added this to the same buffer over here, again, opening up kind of early here, we have HFs floating around. We have a little bit of H plus and some F minuses floating around. So if we take some sodium hydroxide and we dump it in here, because sodium hydroxide is a strong base, it is going to react with the acid part of the buffer. So we will get sodium hydroxide plus hydrofluoric acid. We will then produce sodium fluoride. Again, double displacement reaction. Sodium and the fluoride come together. H and OH come together. That makes water. H and OH. And we again see a couple of things. We make part of the buffer. So we make some more of the buffer here, which was there to begin with, which obviously is not going to screw up the pH. We also made water, which is essentially neutral as well. So that's not going to mess up the pH. And much like what we were talking about above, it's actually what we do not see here, which is why the buffer doesn't really change pH all that much. When we added the sodium hydroxide to water, we produced, as you can see here, a lot of OH minuses really quickly. But here, when we add it to the buffer, no free OH minuses are produced. So same logic, because the OH minus concentration remains relatively constant, that means that the H plus concentration will also remain relatively constant. And by default, what that means is the pH will also remain relatively constant. Again, same idea here. If you actually were following the pH, you would see the pH go up a little bit, but not a giant jump in pH. So really, buffers are able to work because they have an acid part and a base part. So when you add more acid, it's able to prevent the formation of free H plus. And when you add more base, it's able to prevent the formation of free OH minus. By preventing the formation of those guys being free in solution, it allows the H plus concentration really to remain constant, and thus the pH also remains relatively constant. Any questions on that there? So visually, if you were to make a buffer, maybe you make a buffer with pretty much equal parts of the acid part of the buffer, like our example HF, and the base part of the buffer, like our example, the F minus. And when you add acid, it will react with the base part of the buffer, but will then make more of the acid part in my exaggerated drawing here. Acid part goes up, very exaggerated. Base part goes down of the buffer. And same thing occurs if you add base to your buffer. The acid part goes down, the base part goes up. Again, exaggerated drawing here. Acid part of our buffer. And this is why a buffer can work fairly well over a good period of time, because you're sort of regenerating part of the buffer as you're adding, acid or base to it. Is there a limit to how effective a buffer can be? The answer is yes. So let's just say I wasn't paying attention, didn't follow instructions, never happens, I'm sure. But we just continue to add acid, or maybe we add a really, really strong acid. What that's going to do is, if you do this, you're just going to keep eating up the base part, eating up the base part, eating up the base part, until at some point you'll blow through the buffer, basically. And at that point, if you continue to add basically acid after you blow through the base part, you at that point will start to collect a lot of free H pluses, because there's nothing here in the buffer now to take care of those guys. And at that point, you will see a big drop in pH, because you basically blew through your buffer. So actually, when you make buffers, you want to always make sure that you make them sort of correct in terms of the concentration, in terms of the molarity of the acid or base you may be adding to it, to make sure you don't kind of blow through the buffer. So there is sort of a limit to how effective a buffer can be. Again, if you sort of make it correctly for the situation, it should work really well and be able to maintain that pH over a long period of time. Any questions on buffers there? And again, here's just a table of what should go into a buffer. And really the ultimate way a buffer works is, again, preventing that formation of free H plus or free OH minus when you add acid or base to it. And that's ultimately, how a buffer is able to maintain its pH. And as I mentioned before, if you really were following the pH there, you would be able to see the pH change. But what we're talking about here with buffers is we do not see a giant change in the pH. It's able to relatively maintain its pH over a long period of time, but no really big jumps in pH. Any questions on acid, bases, pH, pOH, buffers, how to calculate those things? Okay, then we're off to the next chapter, which is organic chemistry. So we could put our calculators away probably at this point. In these chapters, more so memorization, naming, and those type of things. But obviously, that last chapter had a lot of calculations, so don't throw your calculator too far, as you will need it, obviously, for exam 3. So let's talk a little bit about Let's talk a little bit about organic chemistry. That is the much better word there. Organic chemistry, pretty much the first sentence that you see in every organic book is this sentence right here. Organic chemistry is really the study of carbon compounds. The basis of organic chemistry is basically compounds that are carbons attached to other carbons, and attached to those carbons are a lot of times hydrogens. And along the way, it could be long chains of them, short chains of them. Along the way, we kind of swap out the carbon hydrogen bond and add other things in there. Other things like, we switch out the hydrogen for things like oxygen, nitrogen, sulfur. Some other elements sort of come on, hydrogen sort of comes off. Now, the basis of organic compounds is that carbon hydrogen bond. And if you remember the carbon hydrogen bond, carbon is like 2.5 in terms of electronegativity. Hydrogen is 2.1. Where we do our change in electronegativity, 2.5 minus 2.1 gives us a 0.4. It is a non-polar bond. And the basis of a lot of organic compounds they are basically non-polar. And that means that, we get a lot of problems when organic guys are with things like water, which are polar. There are some organic compounds that can interact well with water. And because we sort of change out some of these carbon hydrogen bonds along the way, we do get what are referred to as functional groups. And functional groups are essentially the part of the organic compound which basically makes it a special type of compound. And what I mean by that is, for example, the simplest sort of functional group is a carbon-carbon single bond, which means everybody there has all carbon-carbon single bonds, no double bonds, no triple bonds, nothing else going on there. These guys are what are referred to as alkanes, which are the simplest sort of class of organic molecules. If you change out a hydrogen and replace a hydrogen with an OH group, for example, this OH group, which is actually a polar group, more negative here on the oxygen, more positive on the hydrogen, something that has an OH group, that is the functional group for an alcohol, which has some different properties than alkanes, which is another organic group. So within organic compounds, there's usually some part of that compound, some type of bond that's there, some type of connection with a certain element that's there, which makes it a certain class of organic compounds. And you can basically identify these guys solely by, that particular functional group. As we will see, as we'll go through pretty much all the functional groups here in organic chemistry, depending on the functional group, might give it a different name. It might have different reactivity depending on what functional group is present. For example, by even having the same elements present, but the double bond being there, these are what are known as alkenes because they have double bonds. If you have the same element but a triple bond, these are what are known as alkynes. So again, slight changes in these organic molecules from the bases of carbons, the hydrogens being bond, do give these guys sort of different properties and different sort of characteristics. Now, an organic compound, as I mentioned, is basically that carbon-hydrogen bond. It can contain other elements, as we will see. Oxygen is very common, sulfur, nitrogen, phosphorus, and any of the halogens that are present. These guys will, halogens, again, group 7 on the periodic table. That's your fluorine, your bromine, your chlorine, etc., your iodine. But the basis of all organic compounds are really this guy, which is carbon. And if you think about Lewis structures, carbon really wants to make 4 bonds. So carbon always wants to kind of make 4 bonds. And that's a good thing to remember, especially in organic chemistry. People, for some reason, when they start drawing these things, which you'll have to do, people want to give carbon 4,000 bonds. They just keep throwing bonds on carbon, 10, 12, however many, and they keep throwing on there. But if you want to draw carbon sort of correctly, you should never, ever, ever go over 4 bonds, and especially an organic sort of compound. And again, it's a very common mistake that people do make. So just keep on piling on those sort of bonds. Organic compounds typically do have covalent bonds because they're really nonmetals and nonmetals together. They have very low melting points and boiling points because, as we talked about, they are basically using that dispersion forces as their intermolecular forces. And remember that is pretty much your weakest intermolecular force. Remember, there's hydrogen bonding, right, which is the strongest. There's dipole, which is really strong. And there is your dispersion forces, which is the weakest. Dispersion forces are pretty much what nonpolar guys use. And if you remember, these are really what polar guys use, both of these guys sometimes. They have the ability to hydrogen bond. A lot of the first organic compounds do undergo combustion reaction, like if you light a Bunsen burner, a little bit of methane, a little bit of oxygen, and you get H2O plus CO2. And you produce, obviously, a flame. They typically are not soluble in water. Water, again, is polar. Organic guys, for the most part, are nonpolar, which means when you put them together, they typically will layer out, where typically the upper layer is your organic guy. The bottom layer is your sort of water or aqueous layer. That's typically what happens. Again, because water is trying to use hydrogen bonding, organic guy is using dispersion forces. And if you remember, like we talked about that saying of like dissolves like. So things with similar intermolecular forces, they're able to really interact well with each other because everybody's trying to interact the same way. Things that have very, very different intermolecular forces aren't really able to participate well with one another because they really are not trying to interact the same way. So difference between organic and inorganic compounds. Many inorganic compounds have very high melting points, and inorganic compounds that are ionic usually are soluble in water, and most do not burn in air. Something like propane is a little bit different. Propane, obviously, as you're familiar with, is used as a fuel. It obviously catches on fire and so forth. Why is that? Well, basically, something like sodium chloride, which is what this big guy looks like there, it's basically a bunch of positive and negative ions, which are in a three-dimensional space with each other and held together by very strong electrostatic attractions. And that is basically your positive negative attraction to one another. That is really a what is referred to as a intramolecular force. And an intramolecular force means within the molecule, which means that is super strong to basically break apart. And they typically will not go into the gas phase. It will not, melt. It takes a lot of force to get it to melt. It will melt, but it will not go into the gas phase. But it has very high boiling points. Something that's organic, which are just held together, say if you got some organic guy with another organic guy, they're both non-polar and they're held together by this dispersion force, which is a intermolecular force. So not intramolecular force, but intermolecular force, which means between molecules. So when you go to heat something like this, it's pretty easy to break. It breaks apart. This guy goes this way. This guy goes this way. They come apart. You heat this guy. It's nothing much is going to happen other than they'll stay together and start to melt because of that really strong intramolecular force. Any questions on that there? Here's a table of some of the sort of differences that we see between organic and inorganic guys. Again, we see very, very high melting points and boiling points in our ionic compound, again, because it's held together by that intramolecular force. Super low, on the other hand, over here in our organic, because they're held together by those super weak dispersion forces, and they're able really to sort of break apart pretty easily. So let's take a look at this here. Identify each of these as being organic or inorganic. It has a high melting point. So again, that high melting point we see in ionic compounds, which would be more inorganic. Again, held together by really strong intramolecular forces. Not soluble in water, that's going to be our organic, which is typically non-polar, and polar does not mix. Has a formula CH3, CH2, CH2. This is carbons and hydrogens, carbons and hydrogens, carbons and hydrogens. That basically screams organic. This is an ionic compound, which means it's not organic, no carbon to be found there. So this would be inorganic. Burns easily in air, that is organic. They go through basically a combustion reaction. Remember, the organic combustion reaction is basically an organic compound plus some oxygen. That's what it means about burning in air, and makes CO2 plus water. Has covalent bonds, that also is an organic guy. Any questions on that there? Okay, so let's get a little bit into some of these organic guys. We're going to start with sort of really the simplest sort of guys that we got going on. And really, they are hydrocarbons. And hydrocarbons, much like the name implies, are really compounds that contain basically hydrogen and carbon together. Our simplest sort of hydrocarbons are alkanes. As I mentioned earlier, the functional group there is really the carbon-carbon single bond here. Every organic guy is again based off of the idea, as I had mentioned earlier, carbon with its 1, 2, 3, and only 4 bonds happening here. So I can't say it enough. Don't go over 4 with our carbon. We also have something what is referred to as a saturated hydrocarbon. So saturated hydrocarbon means that basically that compound has the maximum number of hydrogens that are possible. So if you have a compound like what we have on the bottom there, which is ethane, basically we are taking up a bond here between carbon and carbon, which leaves the carbon on the left only 3 more bonds to get to 4, carbon on the right, 3 more bonds to get to 4. And if it's a saturated hydrocarbon, all of those bonds are hydrogens. So if something is saturated, basically what it means is it has the maximum number of hydrogens that are possible in that particular case. By the way, alkanes have a general formula of CnH2n plus 2. So what does that mean? Well, let's take this guy for an example. This guy has 2 carbons, and that is what N is. 2 times 2 is 4 plus 2 means it should have 6 hydrogens, 1, 2, 3, 4, 5, and 6. This guy that I originally scribbled on had 1 carbon. 2 times 1 is 2. 2 plus 2 is 4, has 4 hydrogens. So alkanes have that general formula. You know, if we had 3 carbons, 3 times 2 is 6. 6 plus 2 is 8. It should have 8 hydrogens and would look something like this. Again, carbons attached to carbons and hydrogens attached to those carbons. As you can see there, 8 hydrogens, 3 carbons. Now, in alkanes, like CH4, which is methane, that is the simplest alkane you could have. The simplest organic guy you could have is basically 1 carbon with basically 4 hydrogens attached there. And there's a few different ways we can represent these formulas. This is obviously the molecular formula. We could also draw this out. This is what is referred to as the expanded structural formula, as you can see on the bottom. This is what is known as the condensed structural formula. Condensed basically just means you don't draw out the hydrogens. It's basically the only difference between these two is you really don't draw out the hydrogens. There's a few other. This is space filled. This is ball and stick, like you were making models. This is basically sort of a 3-dimensional wedge type drawing where the kind of dash line means it goes behind the page. The wedge comes out of the page at you in sort of 3-dimensional space. When we look at something like carbon here with alkanes, and especially, for example, we could see it here with our methane. If we think back to geometry here, this is 1, 2, 3, 4 electron pairs. Also 1, 2, 3, 4 bonds. This guy has what is referred to again as the tetrahedral geometry. And it's why alkanes will sometimes have a zigzag sort of shape. And what I mean by that is you'll sometimes see them drawn sort of zigzaggy like that because they all basically share that tetrahedral arrangement. The second alkane that you could have is 2 carbons and 6 hydrogens. Again, CnH2n plus 2, N being 2. 2 times 2 is 4 plus 2 is 6 hydrogens. Here is our, again, expanded structural formula where we draw out all the hydrogens. This is our condensed formula where we draw out no hydrogens. It's important, though, when you look at this guy, that you do understand the connection, and sometimes it is sort of written like that. Even though it's like CH3 to the CH3, and it looks like here that the H is connected to the carbon there, it is actually, as we see to the left there, the connection that happens here is always the carbon to carbon. And then again, we have our hydrogens connected in to those carbons. So sometimes people get a little confused when they look at a condensed formula like this, and they think that the connection is between the hydrogen and the carbon. A reminder, just like we talked about with sort of Lewis structures, you can't really have a hydrogen in the middle. So remember, if you thought for some reason it was like this, this should not make sense to you, because hydrogen would have too many bonds. So even in the sort of condensed form, it's always carbons attached to carbons, and then everything else pretty much attached to those carbons. Any questions on that there? So in butane, we want to predict the shape at each carbon, and let's take a look at this. So if we look at this carbon here, this carbon here, this carbon here, or this carbon here, truthfully, it doesn't really matter. What you want to do is take a look at the carbon on the left there. It has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. That is 4 electron pairs and also 4 bonds. That is going to give that carbon a tetrahedral geometry. Same thing if we take a peek over there at the carbon next to it. As actually, this one would count for the guy next to it. 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, still tetrahedral. Carbon next to it, 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, and 4 bonds. That guy is also tetrahedral. And lastly here, 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs, and 4 bonds. That guy is tetrahedral as well. They are all tetrahedral in shape, as we were talking about earlier. They all have the bond angle of 109.5 degrees. And that is why they do give this sort of zigzag shape. What we're looking at here is the expanded structural formula. And again, all of the hydrogens are drawn out. You could also do condensed formula here. CH3, CH2, CH2, and CH3. Get that the right 3. And again, to illustrate what we're talking about here, let's go with purple. CH3 is basically these guys right here, CH3. Then we have CH2, which is basically these guys right here, CH2. We then have CH2 again, which is this guy right here. And lastly, we have CH3 there at the end, which is this guy right here. Again, the real difference there is no hydrogens being drawn out. Any questions on that there? We could also draw what is sometimes referred to as the line structure. And the line structure is commonly used in organic chemistry, but we don't really write anything out usually. So for example, this right here is the line structure for this guy. And basically everywhere there is sort of an end are a point is a carbon. So this would be the carbon, this would be the carbon, this would be a carbon, and this would be a carbon. And every one of those carbons would get the 4 bonds by having 1 hydrogen, 2 hydrogen, 3 hydrogen, like the guy at the end. Guy here has 2 lines coming in, which means he would have 2 hydrogens, like the guy right here. This guy also has 2 lines coming in, which means he would have 2 hydrogens, like the guy here. And the guy at the end would have 1, 2, and 3 hydrogens along with the line coming in. Would give it 4 bonds like the guy at the end. Now, typically in line structure, we don't write any of that in. We just simply write that, and that represents basically this compound right here. Question on that? So let's then talk about alkanes that we kind of touched upon a little bit here. Alkanes, again, functional group. Carbon-carbon single bond. A large of them are saturated hydrocarbons. Again, saturated basically means that we have the maximum number of hydrogens that are possible. And they do have that general form, as I mentioned before, CnH2n plus 2. Now, the first sort of several alkanes, which are important to know. Basically, if you got 1 carbon, that is CH4. 2 carbons would have 6 hydrogens. That is methane. 2 carbons, 6 hydrogen is ethane, E-A-N-E. 3 carbons, and that would be 3 times 2 is 6 plus 2 is 8 hydrogens. That would be propane. 4 carbons would be 10 hydrogens. That would be butane, A-N-E. 5 carbons and 12 hydrogens would be pentane. 6 carbons and 14 hydrogens would be hexane. 7 carbons and 16 hydrogens would be heptane. 8 carbons and 18 hydrogens would be octane. Go this way. 9 carbons and 20 hydrogens will be nonane. And lastly, 10 carbons and 22 hydrogens would be decane. You can see that these are all alkanes, A-N-E. Every single one of these end in A-N-E. A-N-E all the way across on all these. Most important thing to do if you want to do probably good in organic or keep up with organic is learn these 10 names as quick as possible. So these 10 names are really important because pretty much everything else in organic chemistry, when you go to name, all pretty much comes back down to these 10 names. So everything that we name in organic chemistry and all the chapters, all the different functional groups, they all really come back down to these sort of 10 names. The only things that change, for example, is kind of the ending. So, you know, if you had this guy, which is ethane, 2 carbons, but you make a double bond, which is not an alkane, but has a double bond. This guy is what is known as ethene, E-N-E, because this is a alkene, E-N-E, based off of ethane. So everything that we name, everything that we come to in terms of naming, all based off of really these first 10. So let's talk a little bit about sort of naming alkanes. when we name alkanes, pretty much it's all about the ANE at the end. They have that carbon-carbon double bond. And typically in organic chemistry, we oftentimes will talk about naming things the IUPAC way. And that's sort of like the formal way of naming it, sort of the proper way of naming it. It stands for the International Union of Pure and Applied Chemistry. They're kind of the guys that make up all the rules about naming things in chemistry and all that. You can thank them. But basically, when we go to name an alkane, for example, let me do this here. And just do it this way. Do it that, do it that, do a little bit of that, a little bit of this guy really quick. Maybe. Okay. The very first thing you want to do in pretty much any naming of organic compounds is you want to look for the longest continuous carbon chain. And what that means is you could start at one end and go the other way. The only thing you can't do is back up. So for example, if I went here, just went straight across, that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So that is 5 carbons in a row. Is that the longest continuous carbon chain? The longest continuous carbon chain does not necessarily always mean the straightest. Let's say I started here, went 1 carbon, 2 carbons, 3 carbons, 4 carbons, and went up. That is 5 carbons. That is now 6 carbons. That is more than 5. So the longest carbon chain in this particular case actually would be 6 carbons. So sometimes people miss that by always going with like the straightest. It's not necessarily always the straightest. You could kind of go this way, go up, go over. Again, the only thing you cannot do is backtrack. So once you kind of commit one way, you got to go till you hit a dead end, and that's it. Our other option could have been, if we wanted to go this way, we could have went 1, 2, 3, 4, and that obviously is less than 6. So 6 here would be the longest carbon chain. The importance of that is that's going to be the base of my name here. So 6 carbons, all single bonded. The base of my name is hexane. And what does that mean for this guy here? This guy is what we call a group. It is a group that looks just like 1 carbon, which is also based off of 1 carbon, which is methane. This is what is referred to as an alkyl group. So instead of methane is missing 1 hydrogen, it is known as a methyl group. And this would be methyl hexane. The other thing that we commonly need to do in organic chemistry, which obviously we'll talk more about next time, is we actually have to give people the location of where this guy is located. And that guy happens to be located at carbon 1, 2, and 3. And this would be what is referred to as 3-methylhexane. Hexane because the longest chain is 6 carbons. Methyl because that is the group that's not part of that longest carbon chain. And 3 is the location of what carbon that group is attached to. As you'll learn about organic naming, it's all about telling people exactly what's there and where you can find it. It's all about location, location, location. It's a little taste of it. Obviously, we will continue on next time talking about more of how to do these guys. Any questions on any of that there that we talked about today?